We've spoken already about our power functions. Really, it's x to the power of n, where n is odd or even typically. So if we consider the odd power functions here, x cubed and x to the 5, we know that x cubed, x to the 5, x to the 7 all behave typically like an x cubed function. The only thing is they get a bit flatter through the middle, don't they? So if we're just going to sketch that x cubed graph, hopefully remember, it's the point 1, 1 or 1, negative 1, 1, 1. So it's those points there where our lines become a little bit flatter and steeper. So if that's an x cubed graph, well then my x to the 5 graph comes up higher, gets flatter in through here, oops, and then comes up inside. Yeah. And then if we're going to apply some transformations to them, well then we just do exactly the same thing. So again, let's start with our xy. And what are our transformations? Reflection in the y-axis. So in the y-axis is about the axis, okay, which means the x value changes sign. A factor of 2 from the y-axis. So from the y-axis is shifting out, stretching out that way. So from the y means my x value has changed. So then it becomes negative 2xy. Translation 2 units in the positive direction of the x-axis, so it's across 2. 3 units in the positive direction of the y-axis, so it's plus 3. So then it becomes, well, we are negative 2x, and I'm going to add 2 and y plus 3. So again, my new x value is equal to negative 2x plus 2. My new y value is equal to y plus 3. Rearrange. So I get x dash minus 2 over negative 2 is equal to x, and I get y dash minus 3 is equal to y. Once I've got these two statements, they can go into any rule that I'm interested in. The rule I'm interested in this case is y equals x to the 5. So in that case, y equals, so if y equals x to the 5, that's the same as y dash minus 3 equaling x, which is x minus 2 over negative 2 to the power of 5. So tidy up a fraction, y is equal to, so that becomes, if you like, x minus 2 to the 5, and I've got 1 over negative 2 to the 5 also, plus 3. So y equals minus 1 on 32 x minus 2 to the 5 plus 3. For my even power functions, x squared, x to the 4, x to the 6 looks very much like a parabola. So if that's, we'll call that x squared. Okay, and that'd be the 1, 1. So x to the 4, well, it gets a little bit fatter through there, but still goes through the point 1, 1. A little bit fatter through there, or flatter. So there's my x to the 4, and that's my x squared. And again, really, you can only really tell the difference if they're both drawn on the same axis. The transformations, let's do it exactly the way in which we've been doing it. I start with the point xy, and it becomes dilation factor of 2 from the y-axis. So from the y-axis is stretching that way, so the x value gets affected by a factor of 2. 2 units in the positive direction of the x-axis, 3 units in the positive direction of the y. So then it becomes plus 2, positive direction of the x-axis, plus 3, positive direction of the y, and a reflection in the y-axis. So in the y-axis, there's my reflection about there. So it's my x value gets affected, which is the whole x value at that point. Yeah. So my new x and new y are equal to those. So now let's rearrange again. X dashed is equal to, we'll go negative 2x minus 2. Y dashed is equal to y plus 3. I get y equals and x equals because that's what my rule is. So let's go x dashed plus 2 over negative 2 is equal to x. Y dashed minus 3 equals y. So now if I substitute those points, again, they're the key statements, into whatever xy function I've got. In this case, I've got y equals x to the 4. The y value is y dash minus 3 equals the x value, x dash plus 2 over negative 2 to the power of 4. So rearrange, I get y is equal to, again, negative 2 to the power of 4, or 2 to the 4. Negative 2 to the 4 is 16. So I get positive 1/16 x plus 2, and take that 3 across. So there's my new function for this one. Okay.